All right, welcome everyone to the first simVITRO webinar series entitled 5 Ways to Test Your Coordinate Systems Before Taking Biomechanics Data. My name is Rob Colburn. I'm from the BioRobotics Lab at the Cleveland Clinic, and we're doing this in partnership with Simulation Solutions, who's our European partner for simVITRO, sales and support. And simVITRO, if you're not familiar with it, is a robotic testing system for orthopedic biomechanics research. And of course, in this process of developing the system and maintaining it, coordinate systems matter for what we do, and we've learned a few things we want to kind of share with everybody else, help communicate some best practices and go from there. All right, so let's dive into this. Why do coordinate systems matter? And I want to make a key focus point here is today we're going to talk about kinematics. So these are the relative spatial relationships. We'll probably do a separate webinar on the kinematic or the kinetics, the load reference frames, but today we're really focused on the kinematics side of things. Understanding how coordinate systems are like shoes. Now you may scratch your head at first, but trust me, when we get to this area, you'll understand how this means and how this is actually quite a good analogy for how we think of coordinate systems and how we use them and apply them. I want to help you distinguish between local and joint coordinate systems because they're different and we use them differently, and learn how to express your joint coordinate systems in terms of the parameters and how people use them clinically and getting clinical meaning out of them. Along the way, we're going to discuss some resources for best practices and identify these 5 ways to test your coordinate systems. And you'll see a couple icons show up. This eye icon, that's one of those questions, one of those 5 ways to test, or the 5 questions you can ask yourself when you're trying to verify if the coordinate system does what you need it to do. And then the little yellow icon is sort of a pitfall area. So common ways that we can make some mistakes when we try to apply these coordinate systems. So I want to kind of point those out so you can avoid them as you're working through your science. Once we've been able to identify these 5 ways to test coordinate systems, we all use these laboratory tools to be able to do this type of research. And hopefully we've equipped you about that point to identify the pros and cons of these tools and how to kind of get the most out of them. To make sure your science is what you need it to be. And then lastly, we want to discuss some exciting new work in this area. Specifically at World Congress, we'll be presenting a poster. So I encourage you to stop by and see the poster or stop by the Simulation Solutions simVITRO booth and discuss that some more with our coordinate system changes that we're making. Let's start here. Motion is complex. This soccer or football player is doing some really impressive things. And if our job was to quantify the motion, it's not simple, just the leg moves or the foot moves up or down, right? This is really impressive work. And I think if I did this, I would fail miserably. And the subtle changes and subtle things that she's doing to maintain control of the ball, I would not have the ability to do that. And understanding those subtle changes and being able to track this is where coordinate systems really come in handy for us. And so our job requires us to record motion and loads, and that could be in vivo, in vitro, or in silico. And then and there's a key distinction here. Some of us also have to simulate motions and loads, and that's a bit different than just simply recording it. And so in that process, we need to make sure our data is meaningful, can be interpreted correctly, and we define and use these coordinate systems appropriately. And this is one of the key things here is when we have certain coordinate systems to be used in certain applications for certain joints, we need to agree upon that as a scientific community so that when I publish a paper and I have numbers and curves in there, that those can be correlated in a way that you can interpret that data and we can build the science from there. The bottom line is that we need to be patient-centric with what we do and with our coordinate system choices and with our research. And we interact with clinicians because ultimately if our goal is our research ends up affecting patient care, the clinicians in the middle of that process, and we need to be able to communicate that clearly and effectively to them. Coordinate systems are like shoes, right? So this may be a bit confusing, but hear me out. I'm not going to go with the one-size-fits-all analogy that would be easy to think of. It's more about time and place. So in this environment, there's a few shoes that you could wear that would work. Probably the tennis shoe, maybe the dress shoe or the high heels. That might be appropriate in here, but the ice skates would probably not be appropriate in this environment. Now, in this environment, if you wanted to join these girls on the soccer field or football pitch, wherever you're from, you'd call it something different. There's really only one shoe that would be ideal for this application. And in this environment of a wedding, I'm pretty sure the clown shoes would not be a good fit. And so when we think about coordinate systems and the environments we're applying them, we need to make sure we're kind of matching the right shoe or wearing the right shoe in that particular application, because it varies and it can be different. So let's look at coordinate systems in terms of defining what they are and what they mean. And I found this wonderful quote from Joe Sommer, and he says, and this is in 2000, notice this date, this will matter later when we look at some of the standards that were developed. In biomechanics, we face two major problems in regard to describing both absolute attitude of an anatomical segment, or a camera with respect to an inertial frame, or relative attitude between two segments across an anatomical joint. And this is the key line: our descriptions must be both mathematically tractable and clinically relevant. And his point is wonderful in that we can define a coordinate system that's mathematically tractable, and we can use it and the math works out great, but if we can't define that coordinate system in a way that a clinician can grasp it and use it in patient care, we failed. Likewise, if a clinician says, hey, this is how I want to define a coordinate system, but the math doesn't work out, then we've also failed. There are two types of coordinate systems we're going to be talking about today. The local coordinate system, which consists of an origin and an XYZ axis vectors fixed in a specific rigid body. And then the joint coordinate system is the relative translations, rotations of that rigid body, one rigid body to another. And knowing that relationship is the joint coordinate system, or JCS, that a lot of people consider it to be. The local coordinate system, again, is these origin and the vectors, and they're fixed in anatomy. And you can see this is from the ISB paper on hip. So we use some anatomy, the ASIS, PSIS, draw some vectors, get our origin. The origin of the femur is at the hip joint center of rotation. So in this standard, we have a local coordinate system that has clinical meaning, and it's defined based on a combination of anatomical landmarks and some morphology. In the case of the hip joint center of rotation, that's a functional motion. We really can't digitize that center of rotation, but we can rotate the femur relative to the pelvis and sort of do a sphere fit and say, okay, this location in space is the origin. When we develop local coordinate systems, one of the first pitfalls we can come into is we need to make sure we can handle missing anatomy. In gate lab, this is not necessarily an issue, but more in vitro testing, cadaver research, or if you're doing biplanar fluoroscopy or finite element analysis, you don't necessarily have the full bone there, and we need to be able to handle that anatomy. Our vectors must be orthogonal, our XYZ. This is sometimes overlooked. We want to talk about that, and obey the right-hand rule. So let's start with the right-hand rule. Most of you are familiar with it, but we'll discuss it here. We have an X, Y, and Z reference or vectors, and the right-hand rule describes the relative relationship between these two. And you can imagine if I had this configuration of my fingers with my left hand, the Y would be flipped the other direction. And so to be consistent and mathematically tractable, we're going to need to say that we're going to obey the right-hand rule for defining our coordinate systems, those XYZ vectors. The trouble with the right-hand rule is it causes us problems when we look at right and left specimens. The superior axis on this right and left side matches. Those are the same, which is good. The anterior is the same, so that's good. But when it comes to that medial direction, on the left side, it becomes lateral to obey the right-hand rule. And this whole thing begins to break down. And this can cause problems in your measurement or control. So one solution that people have used is to have two different coordinate systems, and several of the standards look at things that way, where, if you're using a right-sided specimen, the medial will be that Y vector. If you're using a left specimen, the Y vector will be lateral. But that gets challenging if you're trying to combine your data from two different sides. You have to handle the mirroring, and one's negative and the name changes, or if you're working in a control reference frame or a robot reference frame, you need to think about, well, I have a trajectory. The trajectory is going to be applied from one side to the other side, but I have to mirror things. And so that gets messy to keep track of two different trajectories for each one. The control gets messy. So within simVITRO, the solution we've used is a mirror function. So it eliminates all the control and trajectory headaches, and it makes it easy to combine data from the left and the right sides. And that really allows the user to combine their data in a way that they can communicate it easily in a manuscript and publication. Vectors must be orthogonal, and they must have clinical meaning. And so this is a pitfall because we can get ourselves in trouble if we're not careful with this. When we're defining our local coordinate system, one axis is going to be the strong axis. In this case, we're drawing a line from the center of the epicondyles up through the femoral head. And then our second vector is going to go from the medial to lateral epicondyle. But you can see these are not necessarily orthogonal to each other. And in that case, to make this mathematically tractable, we need to make sure that vector is truly orthogonal. And that's the yellow dotted line. So it's not really going through those two anatomical landmarks, but it's pointed generally in that same direction. Another way this can cause us issues is when we look at the other side. So we can make the strong axis be equal to the medial lateral axis, that's the blue one, and we can look at the green vector, which is what we'd want to go for the superior axis, but to make it orthogonal, you can see that yellow line doesn't pass through the femoral head. And so we need to make sure things are orthogonal, but understand that has impact on our clinical meaning and direction. So you have to be careful when you build these local coordinate systems. So this comes to our first test question, is do I have the right rigid body reference frame? It needs to be mathematically correct, it needs to be unambiguous, and the big thing is that it needs to have clinical meaning when we define these. Fortunately, we don't need to do all this work ourselves. We stand on the shoulders of giants, and the ISB helps us as well. So the first paper that is commonly used these days was published in 1983 by Gruden Sente on the description of the knee coordinate system, and it's used very widely. And then in the mid-90s, Wu and Kavanaugh, as part of the ISB, released a paper looking at how do we define coordinate systems for the entire body to sort of standardize that. And then in 2002, so this is 2 years after Joe Summers' comment, they published for the ankle, hip, and spine very specific coordinate systems for each joint. And then in 2005, they published that for the shoulder, elbow, wrist, and hand. And while these standards are not going to cover every single situation or every single shoe, if you will, they cover a majority of them. And in general, we try to adhere to these as best as possible. So when we designed simVITRO, we thought about it in terms of modules. So it's organized based on different joints. Each joint has specific local coordinate systems for each bone that are already developed for you. That's the right anatomy. All the math is there, so you don't have to think about it. And then even within a specific rigid body or specific bone, you can have different coordinate systems. Because like I said, the ISB standards can't do everything for everybody. For example, we have a regular coordinate system we use, the simVITRO one. We also have the K9 one, and that's because the tibial plateau angle is a bit different on the tibia, and you have to handle that a little bit differently. So we want to make it flexible for people to use, but still try to follow the guidance of the ISB standards. Joint coordinate system is the next piece of this, and that's the relative motion between the two. And here we have a little image of a knee showing how the tibia is moving relative to the femur. But if we define this as the femur moving relative to the tibia, the math is going to be different. The numbers will be different. And if I published femur moving relative to tibia, our data is not going to be able to correlate, and simply because of the definition, not because we got any different results. The translations are the first part of this. Those are going to be based on the local coordinate systems. So if I overlaid the origin and axes of the femur and the tibia, that's the starting point of the joint coordinate system, and everything translates and rotates from there. Those translations could be applied first and then the rotations after, or it could be sequential, as in this graph of you translation and rotation sequentially moving through. After translations comes rotations, and I put a pitfall in this simply because this, I think, is the most area of controversy involving coordinate system definitions in biomechanics. There's 4 major ways to express these: the Euler angles, axis angle, quaternions, and rotation matrices, and we'll go through each of those. And then I want to talk a bit about how to combine the translations and rotations together to form a mathematically powerful way that we can handle the coordinate systems of our entire system. So first, we'll start with Euler angles. And I'm going to jump over here to SolidWorks to this little demonstration I made. So if you look, this is following, actually, let me jump back real quick, I apologize. Euler angles are defined in multiple ways. So we have Cardanic rotations, which are some combination of X, Y, Z rotations in different orders. In order of rotation matters. And then the Euler angles, the classical Euler angles, were really based on celestial mechanics. But they, if you notice, the key thing is the first and last rotation are the same, X, Y, X, Y, Z, Y. And that's how they're a little bit different. And their behavior is a little bit different in terms of the math. But that's the general idea, is you pick an axis and you rotate about it. And so it's very easy to get your head around to understand how this works. So in this case, this blue rotation is my yaw axis, which is following a standard roll pitch yaw. It's a ZYX convention. And with this one, middle axis, the green one, is the pitch angle. So I can pitch this spaceship up and down. It works for boats. That's sort of, this was developed years ago. And the roll axis is the last one. You can see I can roll, and that's in the fixed body reference frame. So if I tip the pitch angle up and I roll, that roll angle globally is shifted, but it's local to the reference frame of the rigid body. And in the same way, if I move the yaw, now I get different rotations out of the other degrees of freedom. So this is very convenient. We can understand it, get our head around it, whether one's in the world or one's in the rigid body. And this middle green one is considered the floating axis. The challenge with the Euler angles, the biggest problem is right here. If that middle angle gets to 90 degrees, I have aligned the yaw and the roll axis, and now I have two ways to create motion, and it doesn't know how to solve it. The other problem that this creates is because I've combined these two rotations where I get this gimbal lock, or singularity it's called. If you imagine you were in this ship and you wanted to turn right or left, there's no degree of freedom to allow me to turn right or left. So the gimbal lock basically combines two rotations in the same direction and removes a third degree of freedom that you want to be able to rotate. And so this is really, this gimbal lock singularity problem we'll find through many of the coordinate system definitions. And that's a challenge we need to work around when we define our coordinate systems. The nice thing about Euler angles is they're easily mapped to clinical meaning. We can look at a rotation about a femur or a tibia, and in those local coordinate system axes, the trouble is we have gimbal lock, and if you're doing Cardanic rotations, that's going to be when the middle axis is at plus or minus 90 degrees. And if you're doing Euler rotations, it's when that middle axis is 0 and 180. The most common form of these rotations is roll pitch yaw. Really, it's a ZYX. It's kind of a back order. And we're going to call that the tennis shoe of coordinate systems. It's used in lots of locations. It's very easy, and it's applicable in many environments. That said, please, please, please don't use roll pitch yaw simply because it's what your motion capture system or your robot or any analysis software you have uses. If you've looked at the situation and biomechanically it's the right order of rotations and it works, then use it, that's fine. But we shouldn't just rely on it because our software puts it out. And at the end of the talk, I'll talk about ways you can use your existing software and make some changes to be able to get the output and inputs in clinically relevant and clinically meaningful coordinate systems. But I see this a lot, and I'm just encouraging us as a community not to do that. Another way we can express rotations is axis angle. You've probably also heard it as helical axis or screw axis. And just like Euler angles picks a single vector and can rotate about that vector in one of the primary axes, axis angle picks a unit vector in some direction, puts a scalar rotation about that vector. And so all three rotations really come down to a single rotation about this unit vector. So this is easily understood. It's really beneficial for instantaneous angular velocity, which we use in some of our simVITRO work. And it's actually well used. This is where the helical axis kind of comment comes from, is it's in targeted situations where your joint is hinge-like. This is really kind of nice. So if you think about the flexion axis of the knee, and we want to look how that axis moves around, axis angle is really great. But as a general tool, like if you tried to apply this to hip, it would get very confusing clinically, and it's not really well suited for that. It also has gimbal lock at 0 and 180 degrees. This brings us to quaternions. They're similar to axis angle in that they have 4 parameters, and there's a vector and the rotation about the vector. It's very computational powerful and efficient, and we love that. Interpolation is easy. and it has no gimbal lock. So this is the first definition I've presented now that is completely mathematically tractable and can be used. The trouble is, it's not intuitive. It's not easily mapped to clinical meaning. And so think of Quaternion as a wonderful tool for behind the scenes to do all your math. But when we present the output or present it in papers, we really should think about it in Euler angles or something else that clinicians can grasp better. And the last way is rotation matrices. Rotation matrices is 9 parameters. It's a matrix. Really 3 rotation vectors are built into there. And you can imagine the Rx rotation is rotating about that first axis, and then some angle about the rotation. You get the sines and cosines appropriately placed depending on which axis we're rotating about. So for this tennis shoe coordinate system of roll, pitch, yaw, it's actually a ZYX rotation. So like those Euler angles, we can just multiply these matrices in that order. And if we did XZX, we would just pick the right matrix and multiply it in the right order. So these become quite easy to mathematically use. They're computationally powerful because of that. There's no gimbal lock, so like Quaternions, you can use them behind the scenes, and they're very wonderful for that purpose. The trouble is if I looked at 9 values and you asked me, well, what angle is that? I wouldn't be able to tell you. It's not intuitive. It's not easily mapped to clinical meaning. But because we can use them behind the scenes, we can encode them, how I've shown you here. We can also decode them. So if I take those 2 elements, the ones I've circled with blue and green, I divide whatever numbers are in those 2 elements, I divide them, I take the inverse tangent, and therefore I can extract the angle or decode it out of a matrix. And that brings us to transformation matrices. So now I can encode in a 4x4 matrix. It's only 12 parameters really. The bottom row is always 0, 0, 0, 1. Again, we're back to our tennis shoes. So we have XYZ roll, pitch, yaw. And here's our Z rotation. And there's our translation vector. Q1, Q2, Q3 is the XYZ. And then we're rotating about Y and rotating about X. And that's how we can formulate and encode roll, pitch, yaw into a transformation matrix. And now once we have a matrix, we can develop a whole kinematic chain of how we're looking at all the rigid bodies in our reference frame. And this could be every linkage, if you're looking at human motion in a gate lab. So we'll start with an interest in the transformation matrix between rigid body 1 and rigid body 2. That's the 3 translations, rotations in red. And that's equal to the transformation at every other linkage in this whole kinematic chain. And every one of these matrices we can encode and decode however we need to in whatever reference frame we want. And that's what we're talking about here. So if you encode a matrix with the roll, pitch, yaw, we need to have different ways to look at that matrix and extract the data of meaning. So we could decode it back with roll, pitch, yaw, but we could also decode it as a knee in the Gruden-Sunte reference frame. We could also decode it as a hip, and that's reference frame when we come out of the matrix. But the thing we need to avoid, which is commonly done, is we consider that each element in this are the same. We look at X, we say, that's probably anterior. We look at Z, and that's about superior, but they're not. And we don't need to say that they're the same. We're going to get ourselves in mathematical trouble if we do that. And if I publish something saying, it's about the same, I call X superior, but it's not really superior, and you publish something where you're actually using the Gruden-Sunte reference frame, we're going to get different results. And it's not because we actually got different results, it's our mathematical descriptions are different. And let's discuss exactly the details of why that is. So we have our roll, pitch, yaw reference frame, and see how the translations are here in that first matrix. And that basically means that we translate first, and then we apply all our rotations. And when we do that, the matrix gets multiplied at the end. We can easily extract those elements of the matrices to get our translations. If we look at the Gruden-Sunte definition, the translations are spread out sequentially with the rotations. And when we try to extract that, it's definitely not the same. Now, if you do the math and if you have angles of 0 for everything, then certainly it lines up. But the reality is we're not studying a straight leg scenario. So these angles have values, and these values change the translation. So we can't say that these 2 coordinate systems are the same. We actually have to do the encoding and decoding process. So this is a subject. We were doing a shoulder study. I want to show you why this math really matters. So he was doing an activity of daily living where he's putting on a seatbelt. So he's reaching over his shoulder, moving it down, and plugging it in. And so we took his data and we analyzed it 2 different ways. And the left-hand plot, we're looking at glenohumeral kinematics using plane of elevation, and internal rotation. And that, I think that was a, sorry, I'm going to deviate from script here real quick. Tara, was that an XYX or ZY? Z? It was XYX type of rotation. So that's one of the Euler angles. And then we could also analyze this data in yet another way, which is looking at flexion, abduction, internal rotation. This is also biomechanically okay. We could look at it this way, but you can see the curves are entirely different. And so if I publish the one on the left and you publish the one on the right, and we don't really dig into those details, we're going to get different results and have a hard time comparing. So we need to really agree upon, for a given joint, for a given activity of daily living, this is how we're going to look at these things, these kinematics. So now we're to our second test question, is do I have the right joint coordinate system? So understanding, do I have the right rigid body relative to the other one? Have I looked at my order of rotations and order of translations? How those get applied? And again, the big question here is, does it have clinical meaning what you've done? The third question is, am I avoiding gimbal lock, that singularity? So Euler angles generally seem to be how people express data, this kinematic data in biomechanics, which is great. The clinicians can get their head around that pretty easily, which is good for communication and collaboration with them. But we need to be careful about the ranges of motion and that we're going to apply, and the joint-specific variations. So you can see in the knee, that middle angle, that beta, if that got to plus or minus 90, we get a singularity. But you think about a knee going to plus or minus 90, that's not really a common test scenario that we're concerned with. And so when Gruden-Sente defined this coordinate system, they've handled that for us and we don't have to worry about it. And so along those lines, you don't have to reinvent the wheel. Where these standards exist, look at them, understand them, and use them if you can. If you have to change them, then you have to change them, but try to avoid it unless you have a good justification for doing it. So those are the first three, understanding you have the right local coordinate system and the right joint coordinate system. And then we want to look at the uncertainty in all this. So if I'm defining the femur moving relative to the pelvis, well, what's the baseline? What's the neutral position that I'm going to define? And it's a ball and socket joint, so it's not obvious. It's not a simple landmark, and there's pelvic tilt variances from person to person. So do we find these things as certain forces or torques equal to 0? And the bottom line for this stuff, again, is the clinical question drives the importance. If I'm going to compare something at whatever, some kinematics at 30 degrees of flexion and one specimen to the other, if I have whatever 20-degree uncertainty in defining neutral, then I have a wide variance in what I'm understanding. But if I'm looking for a whole sweep of flexion angles and the endpoints really aren't as strong in my clinical question, then defining the neutral position is less important. If we look at anatomical local coordinate systems, in a gate lab situation, we all understand there's issues with skin artifacts, landmark identification. They're going to be operator dependent. Trying to understand how the bones move using skin motion is difficult. But it's not limited to that. If you're doing finite element analysis, biplanar fluoroscopy, or taking data from CT, MRI, or cadaver testing, you have the same problem. We say we're going to use landmarks to define the coordinate system, but here's the greater trochanter. So specifically, where is the point on the greater trochanter that we're going to digitize when we build our vectors? Or the medial and lateral epicondyle, where specifically is that point? Because there's lots of vectors I can pass through those points that will give me data, but that will affect my coordinate system. And lastly, if I have missing landmarks, if I don't have the femoral head, then that vertical line going up, where do I place it? Where's the right place to place it? As a result, other people have started to quantify this, right? This is nothing new. Here's a paper from 2000 where they were looking at the screw home mechanism of the knee and recognizing that depending on where you place the coordinate system, you can make that screw home mechanism show up or disappear in your data. We also have issues where variation in that digitization or landmark identification can change these mathematical descriptions. So here's the hip, and that red, or the black X is the true center of rotation of the hip. But if for some reason, one time I defined this, I placed it at the red X location, or if a different person would place it at a blue X location, and I rotated the hip 45 degrees, I would get two different pieces of data. One would say the hip moved anterior. As I flexed it, one would say the hip moved posterior. Both are wrong. It's really the variation in my kinematic definition of my origin. And that can influence our data. And when we publish that, we can get different results too. So we need to account for variation there. And people have known this. This is nothing new. And so we have people looking at hip joint center of rotation. UCLA has done some great work with the tibia coordinate system definition to be a functional coordinate system. And that's the idea of applying these functional motions. Here's another great paper where we're looking at functional joint axes in general. And these functional joint coordinate systems need to be defined. And in simVITRO, we use these in a couple of ways, and we don't have them throughout everything because I don't think the biomechanics community has fully figured this out for every single joint. I think we're working through this. Within simVITRO, we can optimize the origin of the hip and shoulder because it's sort of ball and socket-like. We can also optimize femur origin and orientation. So what that looks like is these graphs on the right. The dotted lines are the kinematics we get, the translations and rotations, if we were to passively flex the knee based on the landmarks that we would digitize just by palpating it. And then we run an optimization algorithm that says, yes, I know here's where you put the landmarks and here's where you think the coordinate system should be. But if we were to move the coordinate system to this other location and rotate it a bit, we can reduce some of these off-axis translations and rotations. And what's interesting about some of this, and we can see this here, let me flip over here. In the internal-external rotation, we actually have the screw-home mechanism still show up. We have this flat line, and then at some point we begin to come back down. And this is just one example of one knee. But that's the idea, is that even the optimization doesn't necessarily remove some of the standard behavior of the joint and how it behaves. We looked at this for, I think it was 7 specimens, and we looked across the different kinematic degrees of freedom for the anatomical definitions versus the optimized. And by optimizing just the femur coordinate system, we're able to greatly reduce the off-axis translations and rotations throughout the passive flexion cycle. Now, one of the new things we're going to be presenting at World Congress, and my colleague Colin Gillespie will be there. We have a poster at World Congress, so please stop by the poster, talk to him, and also stop by the simVITRO Simulation Solutions booth. We can talk to you more about it as well. But not only are we optimizing the femur, but we're also optimizing the tibia as well in a manner that allows us to. And we've actually shown that you can digitize and have different starting points for your optimization, and it all converges to the same location. So really, it's a functional coordinate system for the knee that gives lots of confidence that we can compare across multiple specimens and loading conditions. And this comes to our last couple of tests. We're testing the uncertainty in our coordinate system. So do we have a well-defined neutral position? And is that based on landmarks or local coordinate systems, or is it a neutral load? And are we allowing for kinematic offsets to accommodate for this uncertainty in our reference frames? And again, does it have clinical meaning, right? That neutral position, does that mean something to what a clinician would understand neutral would be like? And the last one, testing our coordinate system, is we need to make sure those definitions are robust across multiple specimens and different activities of daily living. You know, is that anatomical based? Is it functional based? And does that definition create uncertainty in your kinematics, and can you use functional coordinate systems to reduce that uncertainty? So we've gone through all 5 of them. I'm going to summarize them here to make it easy. We have the right rigid body reference frame, the right coordinate system, gimbal lock, well-defined neutral position, and that coordinate system definition. I want to leave it there for a second if anybody wanted to take a screenshot or something, just so they have those. And we'll also be, we're recording this webinar, and we'll be giving you a link out of that so you can watch it later and share it, or share it with your students or whoever would be interested in understanding some of this stuff. Let's look at existing laboratory tools. You have to make a distinction between whether you're controlling or measuring something, and it's very important. So if you were in a gait lab measuring human motion, the control is done by the person as they move. And so you don't prescribe how they move, you're just trying to capture that. And so if you're just measuring and your laboratory tools, software, motion capture, whatever, give you the data in XYZ roll pitch yaw, don't publish it in that reference frame. Please convert it, and we've given you some tools to convert it through rotation matrices to the reference frame that you care about. And that's easy. If you're just measuring that way, you can use the existing tools, just make sure you convert it before you publish it. If you're doing control, this gets a bit messier, because if I control in a yaw reference frame and I say, yeah, well, it's about internal rotation, but it's not, then I've actually prescribed some loads or motions in a reference frame that doesn't have the same meaning. If another lab who was actually using Grun-Sente was publishing their data and it was truly internal rotation, we're going to get different results. So the first question you have to ask yourself, is that tool configurable? If it's configurable, that's great. Choose whatever coordinate system you want, and take your data in that reference frame. And that's sort of the model we've chosen with simVITRO, is try to make this flexible for all our users to choose whatever reference frame they need to get the biomechanical data they need, to answer those clinical questions. But we also understand there are systems that are not configurable. And so then you have to ask yourself, can you sort of trick it into, being what you need to be? And this applies, control is not just robots. Control could be finite element analysis software, rigid body dynamics software. If you're prescribing how things move, you need to make sure that you're moving and controlling in those right reference frames. So one way to trick it, depending on the software, is you might be able to convert the inputs and outputs. And the idea is you start with the reference frame you want. If you're trying to prescribe motions, you convert over to roll pitch yaw if that's all their system uses. And then you prescribe those motions in roll pitch yaw. And then at the end of the day, you get your outputs out and you convert it back to the reference frame, the clinical reference frame of interest. If you can't do that, then use your tool with caution, and please, please, please report that in the publication when you're looking at methodology, so that when we're looking at your data, we understand the limitations and understand that when we're comparing to our data that it might not line up, but it's not because either group is doing something wrong necessarily, it's just our definitions are different. Within simVITRO, how we handle that is, this is one of the setup screens for configuration, where you can define all the landmarks, and we have pictures that show you which points to digitize. And then we want to not hide anything from any of the users. All those static transformation matrices are available to you. We also have the ability to do functional coordinate systems, and those optimization matrices are there for you to create, modify, or add to, or use our existing tools. And then even within the coordinate system of a local coordinate system of a rigid body, like I mentioned before, you can actually have different local coordinate system definitions. So we want to give you all the flexibility you need to get the data you need. And I'll just point out, this is, of course, we're talking about simVITRO, but there are labs that don't need that tool, right? There's plenty of other use cases for coordinate system definitions that matter. And for those other labs, if you have tools, make sure you can get flexibility out of your tools for doing that type of research. At this point, we're to the point where we're looking for any questions, if anybody has any of them. Also, if you have any suggestions, ideas for future webinars, things you would like us to discuss, we're all ears and want to serve the community and provide those answers and tools as needed. Well, that's good. I must have been very clear. I don't see any questions coming through. So that was clear. All right. Well, what we'll do, and the other thing I realized I didn't put into here today, and I will do this also when we send out the link for how you can view this independently at your leisure, is I will put some links in that email to some of these standards, the ISB standards and the Grun-Sente and those other papers. So you can look at those. There's also a wonderful website called Euclidean Space that's been very helpful for us, that allows us to look through all these mathematical definitions and make sure our math is all correct, all mathematically tractable. And the folks that create that website have done a phenomenal job. So we'll give you some links to that as well. So as you embark on this work yourself, you have those tools available to you. Great. Well, I think that's it. Thank you so much for joining us. We'll catch up with you later.